Doing this question off the back of doing 4B, the previous question to this, and it absolutely astonishes me that that was 4 marks and this is 3 marks because the amount of effort required is just ridiculous. That 4B for 4 marks was like over 10 times more work. Because here we're trying to show there's no stationary point, so we need to differentiate, but we've just got two things. We've got the result for how to differentiate arc cos, and we can just quote it. We're not being asked to do it from first principles or anything here. I will talk about that at the very end, however. And then it's just an application of the chain rule alongside that. So we differentiate the outside, which is then going to give me minus 1 over, you keep the inside the same. So I just replace x by a half x. And then we times by the derivative of the inside, which is just a half. And this is going to give minus 1 over 2 square root 1 minus a quarter x squared. And of course we could factorize out the quarter if we wanted. Yeah, let's do that. Why not? If I do that, then I would get a half and it would end up giving me minus the square root of 4 minus x squared. Another way to think about it is you can bring the 2 inside the square root. That's maybe the easier way of thinking about it. Then we just times through by 4. Okay, so now to show there's no stationary points, well, this is going to equal 0 for stationary points. But there's no solutions to this. The left-hand side, that's this bit here, can never equal 0. Or if we multiply through by this expression, we would get minus 1 equals 0, which is a contradiction. I feel like that's enough. So left-hand side can never equal 0, no solutions. Therefore, C has no stationary points. Okay, before I move on, I'm just going to show from scratch how you differentiate this, how you get to this formula here. Without the half though, we'll just use the chain rule for the half. So if you have y equals arc cos x, differentiate it, we rewrite it as, sorry, 2 c's here. I would write cos y equals x and then differentiate x with respect to y. I get minus sine y. And that means dy by dx is going to be minus 1 over sine y. But sine squared plus cos squared is identical to 1, which means sine squared is 1 minus cos squared, and I can sub in for sine y by taking the square roots. Square root of 1 minus cos squared y. We actually don't do plus or minus here, we just take the positive square root. This is our principal value. It's based on the restricted domain under which we define arc cos. Not going to go into more detail on that. But then you can see when we now because x is cos y, we sub back in and we're going to get this result. So that's where it comes from. But like I said, you do not need to do all that effort in this question. You can just use the result, use the chain rule, get it, set it equal to 0, just explain that it can't equal 0, and we're there. Now we're told the normal to the curve at the point when x is 1 crosses the x-axis at point A and the y-axis at point B. O is the origin, and we're asked to show the area of the triangle OAB is this. Okay, well, I think it's time for a sketch. I'm actually going to sketch our function. If you're doing further maths, I would strongly advise you get yourself a graphical calculator and in an exam you just draw it out. I still think it is a good idea to draw it out. I also strongly recommend that you practice sketching because it's such a useful skill to have in certain situations, and I think it's actually pretty fun. And it does just develop your understanding as you practice these things. So I want to draw y equals arc cos x over 2. Now, I'm first of all actually going to draw y equals cos x. Like I always forget these ones because I just don't use them enough, but I know how to derive them. So cos x over its restricted domain looks like this. This is how you make it a one-to-one function. because we don't want to include that because then it wouldn't be 1 to 1. And then that will help me draw the inverse. From that, I can then do a transformation to get our actual curve. So we'll just pick a few points. We've got here, this is going to be pi over 2, 0. And then this point here is pi minus 1. And here I've got 0, 1. Now for the inverse, it just swaps around. I'm going to get 1, 0 here. I'm going to get minus 1 pi here. And I'm going to get 0 pi over 2. It ends up looking like that. Now if I want to make it arc, let me write it as arc cos because they do in the question. Arc cos x over 2. So x is being replaced by x over 2. This is a stretch by factor 2 in the x direction. So it's just going to end up looking a bit like that. And suddenly this is going to become 2. This is still going to be pi over 2. This is going to be minus 2. And up here is pi. I think that's just quite fulfilling personally to draw that out without any kind of, reference to software. So we're then being asked about the normal at point x equals 1. So that's going to be here. And remember, the normal is perpendicular to the curve at the point. We've got the tangents like this. I don't want that. I want the one that's at a right angle. Now, it's quite hard to know, does it cross the axis for positive y or negative? And we'll be able to investigate that a bit later on, but it ends up being negative. So what we're actually trying to find is the area of this little triangle here. Okay, and this helps. It's not essential in this question. Obviously, I've spent quite a lot of time talking about it in an exam. You don't want to be doing this. You just want to use your graphical calculator, or maybe just go for it. But if you can kind of just visualize what's going on, I think it helps. Now we're looking at when x is equal to 1, and we're going to get y is equal to arc cos of a half, and that ends up being pi over 3. And because of pi over 3, that's cos of 60 is a half, but of course you can put it in your calculator. And we've worked out what dy by dx is. Of course, you need that result from before. And I'll use this version here. I'm going to get minus 1 over the square root of 4 minus 1. I'm going to get minus 1 over root 3. Remember, that's the gradient of the curve at that point, the gradient of the tangent at that point. So the gradient of the normal is the negative reciprocal. Therefore, it's going to be root 3. Now we use y minus y1 is equal to mx minus x1. So y minus pi over 3 is equal to root 3 x minus 1. And that means y is going to equal root 3x. I am going to write it in the form y equals mx plus c for a second, plus pi over 3 minus root 3. Now, even if you didn't draw the sketch, you'd be able to see at this point that we're going to get a negative intercept because pi over 3 minus root 3 is negative. So that's just something to be aware of. Meanwhile, we're going to get a positive x-intercept. So I now want to find points A and B. Remember, A is where it crosses the x-axis, B the y-axis. So up here, A, here, B. So let's look at A. That is going to be when y is equal to 0. And which one should I'll probably put it back into the expanded one. So that means root 3x is going to equal root 3 minus pi over 3. So x is going to be 1 minus pi over 3 root 3. And then x equals 0. Y is then just going to equal pi over 3 minus root 3. And we've got everything we need now. So I'm just going to draw this triangle out in isolation. Its base is 1 minus pi over 3 root 3. And then remember that value for y is going to be a negative quantity. So if I want to turn it into a length, I need to actually make it root 3 minus pi over 3. Okay, that's quite subtle, but you'll just get the wrong sign for your area. You'll get a negative area if you do not do that. Our area is then a half base times height. And let's just have a little look at what we're trying to get to. So they want us to factorize out a 1 over 54. And I'm going to do this in stages. Let's just have this alongside as we do it. So I've got my half. The next thing I'm going to do is factorize out 1 over 3 root 3. I know we're aiming for 54, but let's not worry about that too much. Let's just make the brackets a little bit nicer. Then I'll get 3 root 3 minus pi here. And then from the second bracket, I'm going to factorize out a 1 over 3, which will give me 3 root 3 minus pi. Actually, it's the same thing. Multiply these out, I'm going to get 1 over 18 root 3, 3 root 3 minus pi times 3 root 3 minus pi. At some point, I'm going to have to also factorize out another 1 over root 3, because that will get me to 54. 18 times 3 is 54. But I'm just going to leave it for the moment, because I feel like this is optimal to multiply out. 3 root 3 squared is 9 times 3. It's going to be 27. Then I'm going to get minus 3 root 3 pi, and another one, I'm going to get minus 6 root 3 pi, and then plus pi squared. Okay, just to finish then, I am going to factorize out another 1 over root 3 out, which is going to give me a 54 here, and I need to times through the bracket by root 3. And this gets it in the right form. I actually think this is like a slightly nicer way of leaving it, personally. But they want the denominator rationalized, essentially. So I'm going to get 27 root 3 minus 6 root 3 times root 3. That's going to be 18. And then plus root 3 pi squared. And that is our area. You don't need to, but you could say P is 27, Q is minus 18, and R is equal to 1. So there we go. We've used the derivative that we found in the first part. I've done a little sketch, which, as you can see, wasn't essential, but it gave us a bit of understanding. The main thing is recognizing that y value of b, the y value is going to be negative. So try and flip it around. If you miss it, you're just going to get the negative of the required answer. Although you might not quite, well, yeah, if P, Q, and R all end up being negative, you know something's gone wrong with the area. And then you might realize, oh yeah, okay, I've made a little mistake. But if you can spot it a bit more quickly, then that's brilliant. And the sketching was good fun along the way too, and useful. Like, you know, you can see how you can construct such complicated functions just by building up from functions that inverses and then doing transformations. We've got our area, so we're there. Well done.